Hello, welcome back to Larry's Classroom. Today I'm going to discuss with you an antenna project that I have in mind. And what I'm going to try to do is build a 3-element Yagi for use on the 10 meter band. And it's going to be, I'm not going to use tubing, I'm going to use wire for the elements, and I'm going to create a structure out of PVC pipe to support these wires. So it's probably a little bit different than something you've ever seen, and I don't know, we're just going to see how this works out. First we're going to talk a little bit about the Yagi design equations, which you've probably seen before, but this is going to be a 3-element Yagi. We're going to have a, I think I make that a little bit bigger so you got a little more room to work to talk about things here. We'll have our director, which I'll just put a D by that. I'll have our driven element, which we'll call DR. And I'll have the reflector, which we'll just call R. Now, I'm going to build this antenna. My goal is to use this antenna at 24, or 28, I mean, it's 28, not 24. 28.420 megahertz. That's kind of the center frequency you want to optimize it at. I'll certainly use it probably beyond that, but that's the frequency I want to design it at. We have to figure out the length of each of our elements. Well, for the director or driven element, it's just like a dipole. It's basically the driven element same formula as a regular dipole halfway, 468 divided by the frequency in megahertz. And when I use the 28.420, I end up 468 divided by 28.420. That ends up giving me a number of 16.47 feet, which is pretty close to 16 feet. 16 feet, 5 5/8 inches. So that'll be our director length. Now, the reflector is usually designed to be 105% of that, so we do 1.05 times the 16.47 ends up giving us 17.29 feet, which works out to 17 feet 3.5 inches if you convert it. So that's 17 feet 3.5 inches. That's pretty close to what it comes out. So that will be my length of my reflector, my length of my director, of our driven element. Now we need to calculate the length of the director. Now the director, standard formulas I looked up on the internet, anybody can look up in them, is about 95% of the driven element. So 0.95 times our 16.47 gave me, when I worked that out, 15.64 feet. And when I converted that, it basically came out to be 15 feet 7 3/4 inches. So now we've worked out the length of each of the elements for my 3-element Yagi. The driven element, 16 feet 5 5/8. We did that with a regular half-wave dipole formula. The reflector, 105% of that, we end up with 17 feet 3.5 inches. The director, 95%. This This increases it by 5%, and the 95% decreases it by 5%. So 0.95 times our driven element length, we end up with 15 feet 7 3/4. You see that each one, this is a little longer, this is a little shorter. So those will be the lengths of our elements. I guess I'll put this frequency, which I want to use it back up here. My design frequency, we'll call this 28.420 megahertz. Now the spacing, we need to figure out the spacing. The recommended spacing is 0.2 wavelengths. I'm going to use an L to represent wavelength. So that's going to be about 0.2 times the 10 meters. 10 meters is, what's that, 35 feet or so. Yeah, it's going to come in the 7-foot range. But let's calculate that. We want to, if we want the wavelength in feet, wavelength L in feet, we use 984 divided by the frequency in megahertz. So when we, and now I want these to be 0.2, so I extend the formula a little bit. I go 984 times the frequency in megahertz, frequency, times 0.2. So this will give me the wavelength in feet of my frequency. This times 0.2 will give me my 0.2 0.2 wavelength spacing that I desire for my elements. So I'm going to put some dimension lines here to kind of anyway, when I worked that all out, I ended up with 6.92 feet, and when I converted that to inches, I got 6 feet 11 1/8 inches. 6 feet 11 1/8 inches. So my antenna is going to be roughly 12 feet long. Well, no, it's going to be about 14 feet long, almost 14 feet long. It's going to be a little over 17 feet wide. Now my plan is to build this out of PVC pipe, and I'm going to attach wires to the PVC pipe. So what I discovered, if I take a piece of PVC pipe and I bow it, just kind of playing around with it, if I make and attach it with a string, which I'm going to use paracord, and if I say the length of that string is equal to 0.96 times the pipe length times the pipe length, nothing critical about that, but that gives me a dimension which seems to make the pipe bow stiff enough for my desired purposes. So what I'm going to do is I'm going to cut my pipes. I'm probably going to cut the pipes, you know, about 6 inches longer in each of these lengths. And then I'm going to make 3 bows with that, using that 0.96 length, and you can, that's not critical, just bend it what's comfortable for you. And then I'm going to cut my wires, probably going to make the wires, probably a little bit longer. Maybe I'll start with a 16 foot and a 16 foot 9, and I'll probably add about 4 inches to each one of these. Anyway, my wires, I'm just going to lay them in here in the inside of that bow, and I'm just going to use electrical tape to tape them to it. So I will have, this is, because it's not a large diameter to length ratio, this antenna will be a little more narrow banded than one made with tubing, but still I'm hoping it'll be kind of inexpensive to build, and I'll be able to tune it and get it to do what I desire to do. So we'll make 3 of these, each slightly different in length, to match up this. And I intend on feeding my driven element just, the director and the reflector are just solid uncut wires. The driven element, I'm going to cut the wire in the middle, and I'm going to hook it down to my coax, and I'm going to wind me a coil for what, like they call a choke or ugly ballon. And that's my plan, to try to drive it that way. And then after I got it made, I'm going to probably use an antenna analyzer and trim the lengths to try to get it best I can working right there at 28.420. I'm going to erase these dimensions now. And I'm going to talk a little bit how my plan are to build this thing. Well, the bows will have a T in the middle. So each of my bows will have a T in the middle. And of course, that will be to attach it to the boom that I'm going to have. What I'm probably going to do, drill some holes near the end of the bows. And I'm probably going to try to find me some small metal S hooks and hook in there. That way I don't have a sharp edge for, this is going to be paracord for my string. My idea is by having we'll kind of expand this a little bit. If we have an S hook, a metal S hook hooked in there like that, it gives me a smooth edge with which to tie the paracord to so it don't cut easily. That's my plan, and this stuff is subject to change as we construct it, but we'll see how it all goes here. I'm going to sketch out a little bit of my ideas on how I'm going to make this thing, and these things will probably not be exact when I actually build it. Things will change. I'll make decisions. Well, I'm going to start with the 3 bows. I'm not going to draw the string down. I'm just going to draw the 3 bows with a T in them, and there'll be a little short coupling and a T on the boom. Yeah, we're going to change that a little bit too, try to make it a little more easy to see. Then we'll have another section of the boom, which will also be pipe. I think I'm probably going to make the bows out of 1/2-inch pipe, PVC pipe, and I think I'll probably make the booms out of 3/4 inch. It's going to have some bracing on it. That'd be pretty floppy by itself. And near the center, I will have another T. Going to be 2 T's near the center. 1 T will have a pipe, probably going to go up about 4 feet or so. And I'll probably use some S hooks to hook into that. And there will be paracord supporting all my pieces. So we'll have a whole bunch of guy wires going down to hold up the elements so it ain't too saggy. And I'm gonna I'm going to get those out of the way right now. Draw them in when I'm done here. And I may buy a piece of, you can buy these fiberglass sign posts pretty inexpensively at the Home Depot or Lowe's. And they're about 7 feet long, but I may cut off a piece, put it down in here to make this thing a little stiffer, maybe wrap some tape in 3 or 4 places to make it fit a little tighter. And I may even have it stick up a little bit so that I put S-hooks around that maybe. Anyway, I'll have 3 bows. And of course there's going to be a coupling pointing up for each bow. And I'm going to have another coupling, of course, pointing down for something to rotate it on, to attach it. Alright, I may just run a pipe alongside and some clamps. I haven't decided that for sure yet. Another T at the end here. I could use an elbow, it wouldn't need to be a T. This thing's probably going to be kind of, let's shorten that up so it looks a little more like a little more proportional. I'm going to kind of draw a top view of this thing. Here's one bow for the director, another bow for the driven element, another bow for the reflector, and we'll have this pipe coming up, which would be this pipe right here. Well, let's put it on the other side just like I did in that drawing. And there will be paracords going here to here, to here, to here, to here, to here. This is to give this thing some stability, and I may run a paracord right to the center. I probably will, to help make it stable in that direction too. That way it's kind of supported from the top, all in a central point, so that the forces kind of balance each other out and hopefully keep it fairly straight. Anyway, I'm going to cut some pipes and glue this all together, and I'll probably take some more film of it to show you a little bit more about what it looks like, and then I'll put it up. I'm going to try to get this about 17 feet or so, about a half wavelength on 10 meters. And it's probably just going to be stuck in a tree or something. I haven't really decided exactly on that, but I'll probably make some temporary pole up about 12 or 13 feet that I can raise it up on to adjust the lengths. And if I get it, I'll probably get it close as I can at that distance and put it up at the 17 feet and use it however it comes out. But we'll see how this all works. I'm looking forward to trying this out. And, you know, it's going to be kind of flimsy. But I'm trying to see what I can do with something simple. Anyway, we'll give you some more information when we get there. So here is my PVC and wire element, 3-element Yagi for 10 meters that I'm working on. You can see it's a PVC frame, PVC pipe, and you see here I've made the elements just out of wire, just taped them to the top of the pipe. This is a pretty flippy construction, so I put a lot of stays on it to there actually are, let's see, there's a stay going to every corner, 3 on that side and 3 on this side, and there's 1 going to each end, so that's 8. And then I found that this upright was kind of flimsy, so I have a stay going from the top of this to the
you know, out about 2 feet on each member here to stiffen this up. And you see here I've got a little plate with 8 holes, and I have these little S-hooks in it. I have a piece of fiberglass rod down through the middle of this center vertical section, which I've tied all these stays to in order to make it a little bit stiffer. This fiberglass rod is it's basically a fiberglass reflector rod that I purchased at Home Depot. And other than that, all of these PVC pipes are nothing inside of them, just in this vertical one to stiffen it up. And I got four stays on it to stiffen it up, and then from the disc up here, I got one to each, the end of each element plus the end of the boom. I got this 2x4 cut in half, 2 4-foot 2x4s, and I have them fastened together with lag bolts here. And I've attached the antenna to the boards with little one strap EMT straps, which seem to fit real nice on this 1/2-inch PVC. And I plan on feeding this like a regular dipole. Here you see in the center where I've cut this. I will feed this with a piece of coax. I will wind a choke at the end of the coax. I'm going to use a piece of coax that I'm going to make that to be 1 wavelength in length, so that I can put my antenna analyzer on it and get a repeat of the actual impedance at the antenna, because my goal here is to get this thing. I don't want to use a tuner on this thing. I'm going to, depending on what the SWR is, after I've connected this feed line with a choke and measured, I may wind a balun to go up here at the feed point to match it to the 50 ohm coax a little better. Underneath here, it's kind of hard to see, I'll give you a look at that when we get it up in the air, is a pipe flange which will screw onto the top of the water pipe mast that I've made. And here you see the end of what will be the director, and you can see that it goes right along here uninterrupted all the way out to the other end of the assembly out there. And here's the end of the driven element, which, like I said, taped them all to the top. It's cut in the middle, and then I have another piece just like it goes out to the other end of the thing. So that's where will be the feed point. And this is the reflector end. It's a little bit longer, taped to the top of the wire, or of the plastic pipe frame. So this is something I hope to get on the air pretty soon and see how effective it is. There you see how this we followed that director the whole way. I'm gonna go from here's the outboard end of the driven element. Goes back to the center here, where I've got it cut, and goes on out to the other side of this framework. Here's the other end of the director. The director and reflector are just continuous pieces with no cut in them, and I space them. The spacing from the director to the reflector is 0.2 wavelengths. The spacing from the director to the driven element is 0.2 wavelengths. From the driven element to the reflector is also 0.2 wavelengths. You can see this thing is kind of flippy-floppy, but we'll see how it holds up when we get it up there. A little bit different construction than you've probably seen before. I thought I wanted to experiment and do something kind of a little more interesting. Anyway, like I said, I'm going to make a 1 wavelength long feeder to go down near the ground so I can connect antenna analyzers to the end of that and read the same impedances actually at the feed point of the antenna. And then I will make a decision depending on what SWR I get, what feed point impedance I have, whether I want to put a balun at the feed point. There are other ways to feed these things. I'm going to feed this one just like a conventional dipole, and we'll see what happens. Looking forward to trying this out. Thanks for... We'll give you some more information after we get it up and try it out on all of these endpoints here. This is just parachute cord that I've used for stays, and I just kind of tied it around the end here, and I got that little aluminum plate at the top, which is, get a little look at that. You can see that little aluminum plate, got the S hooks on it, and that just slides over the top of that. You see it slides right over top of that little fiberglass rod there. Anyway, I'm going to take all of these tied off ends, and I'm going to tape these down with electrical tape to, to help keep them from coming loose when we're in operation. You could do, put super glue on the knots or use hot glue or something. I'm going to do just electrical tape on this one and see how it goes. Anyway, hope you find this thing interesting, and we'll give you a little more information after we actually get it up and try it out. Well, here is the SWR chart from the Rig Expert Antenna Analyzer, and this is before I did any trimming on the antenna, and I started out designing it so that it should be about 7% low in frequency initially, which seems to be pretty much where it came out. So I ended up trimming about 6 inches off of each element on this antenna, and I trimmed 4 inches the first time and 2 inches the second time, and this is off the driven element. And I trimmed 95% of 4 inches and then 95% of 2 inches off the director, and 105% of 4 inches and then 105% of 2 inches off the reflector. So it was proportionally being reduced in size. I also, the antenna is about 17 feet off the ground, and I made a 1 wavelength piece of coax coming down from the antenna, and I got a choke in the end of that, which I think I have 7 turns at about a 6-inch diameter. And the reason I made it 1 wavelength is so that the impedance of the antenna would repeat very accurately at the other end of the coax where I'm actually attaching the antenna analyzer. Now here's the SWR on that 1 wavelength piece of coax standing out there near the antenna using the Rig Expert analyzer. And what I have, the minimum SWR of about 1.14 at 27.980 kilohertz, and the 1.5 bandwidths right here to right here is from about 27.3 kilohertz up to 27.3 megahertz actually, up to about 28.6 megahertz. And what is that? That's about 1.3 megahertz of bandwidth, which is surprisingly good actually. And this is outside the antenna. Now, if I come inside by the radio, I haven't changed anything on the antenna here, but I have 100 feet of RG58A, which is not a particularly low loss coax by any means. And you can see here that the 1.5 to 1 bandwidths, which the lower is right here and the upper is right here. This is from about 27.1 megahertz up to about 29.6 megahertz. We got a significantly greater bandwidth here of actually, what is this, 2.5 megahertz? And the reason for this is because of the losses in that RG58. Losses always improve your bandwidth, but they also waste power. what did we see? Our minimum SWR reading inside the shack with the 100 foot of RG58 was at about 27.740 megahertz, and outside it was about 27.980. So it actually changed where the minimum SWR was too, and outside it was 1.14 minimum SWR, inside 105. Well, again, the losses improve your SWR. That does not mean it's a better antenna. It just makes it a little easier to match. Now I could probably improve this. This RG58A, 100 feet of that, this frequency probably has about 2.5 dBs of loss. And 213 has about half of that. I could buy 213 and I would probably gain another, another 1.2 dB out there. Got the loss probably in approximately in half, so they're having 2.5 dBs loss, maybe 1.25, which it's meaningful, but it's not. If you're hearing me well, that 1.25 dB, you probably won't notice it too much. And here's an interesting thing: if I looked at the impedance outside without that 100 feet of RG58, right in here, about 28.4 is where I want to operate this antenna, and you can see that it is not resonant. At 28.029, we got a resonance here. You see that the resistance is up here in the yellow, and the reactance is the blue line, and you can see that the blue line crosses the zero threshold. So my antenna is resonant. The capacitive reactance and the inductive reactance are equal, or both zero, I mean. So we have a resonant effect at that point. Now, notice we have a single resonance at 28.029 kilohertz, or 28.029 megahertz, excuse me. If I look at inside of the 100 feet of extra 100 feet of RG58 in there, the losses have changed things. I have a resonance at 27.715 megahertz, which is about 300 kilohertz below what I had outside. So the coax has transformed the impedance a little bit. The losses have had an impact on this. It's also showing a resonance at 28.4 megahertz, which is my center line here, which is roughly where I'm using this antenna the most at. It's interesting that the extra length of antenna change, or extra length of coax change that resonance point. I probably want to trim this antenna a couple more inches to get this more natural resonance point up to there where I want to use that. And that would be, let's see, that would be moving that up about, that would be almost 700 kilohertz from here to here. So after taking into account the losses because of the extra coax, I could probably run pretty much the whole 10-meter band. Of course, up in here where the antenna is no longer working like it's supposed to be, it's not going to have the same amount of gain that it has in this area where it's designed to operate, but it still probably work okay. But it's been quite an interesting experiment, and this really surprised me to see this second resonance point that's not there when I don't have that extra 100 feet of coax. Now, there is a second resonance point up here, about 30 megahertz. I don't really know why that is, and another one down here too, but this one is pretty close to where the length of the antenna is meant to be, so that's the one I probably consider to be the the real resonance of the antenna. And this improved SWR, I could reduce the losses, like I said, by putting 213 instead of RG58A. RG58A is a cheap coax, but it also, when you damage it when you're doing experiments, you ain't out much. The 213 is 3 to 5 times the cost. I don't know that I want to spend 3 to 5 times the cost to get 1 or 1.5 dB. Now, your feelings may be different about that. And if I was trying to chase the rare DX that couldn't hear me, maybe I would think it was worthwhile, but it's not something I do too much of. Anyway, it's been interesting. We'll look at some other aspects of the antenna here in a minute.
So I made some changes along the way on the construction of my PVC pipe and Yagi and wire Yagi. And one of the things you might have noticed, rather than a single boom with all the pipe glued up this way, I added some end pieces here like this. And the reason I did that was because I found after I started assembling this, I had a very difficult time maintaining the spacing. So I used some T's and more pieces of pipe to maintain the spacing on the end of the antenna. And I did not put a cross string wire to create the bow. What I found, because it was all pretty floppy, I put an upright made of PVC, and inside that upright I put a piece of fiberglass, which was a stake for a reflector that you put next to your driveway that I picked up at the Home Depot. And let's see if I can kind of draw. Here's the. We'll try to draw each of these. My particular artistry ain't that great, but I had that upright, and then the three cross pieces and these end pieces that maintain the spacing at the ends of the dipole, or of the elements. On the top of the side, right, I just took a piece of aluminum plate, drilled a hole in it to fit over this this fiberglass rod that I had in the center of this upright piece of pipe. I guess I got to put the boom ends in here too, so it kind of looks like a 4 squares when you get it glued together here. And I drilled 8 holes in this thing, and from that I put the little disc is here. I put paracord stays to, and you'll see this in the video of the construction portion that I just and that helps maintain a little bit of, so it doesn't sag like a frown, shall we say. But what else? Okay, it was pretty floppy in the center. I was going to have a piece of PVC pipe going down to mount it, but that didn't look like it'd be suitable. So what I did is let's see, I'll see if I can draw this. In such a way that it's really visible to you what I did here. So I put a 2x4 and another 2x4 crossed it. So I put together a couple 2x4s. These are 4 foot long each, so they came out to, you know, roughly here on, and that gives me a little bit more stability, especially in the direction of the boom. These were bowed up, all the cross pieces with the elements, so they didn't sag quite so bad. And then, of course, because the difference in height between these two 2x4s, I put some uprights on there, short uprights. So if you looked at this from the end view from this end, you would see the end of this 2x4, another one, these are wood, you know, like that. And then they got these uprights going up that so this cross brace here, the support for the center element, came across here, and I used a couple of you know, one-legged conduit clamps to screw into the 2x4 to hold the antenna to this 2x4 cross brace. So those would have been right here. And the center boom, which really went right in here, and that's kind of why I need the spacers to make things more or less flat along the bottom. And of course there's a couple of the cross braces here, or one-hole clamps holding the, so I've got 4 of those, a clamp here, a clamp here, a clamp here, and a clamp here, holding the antenna to this wooden cross brace thing that I put together. And what else? I on the bottom of this thing, I attached it to a pipe with a floor flange for the pipe to screw into, and that's got, you know, 4 holes in it. So I got 4 lag bolts that go right up through the 2 pieces of wood to hold together. And I did put some glue in there when they go together too to help make it stronger, but that was probably not necessary. It's been an interesting project. I'm happy with the way it's going so far, but if you watched the video, you saw where I had what should I say, a better match. Oh, okay, when I was tuning the antenna, you saw that in the video. Well, I made a piece of coax with a choke, and the ends are soldered to the center driven element, and I've got a coax connector here, and I adjusted the length of this piece of coax to make it exactly one wavelength, as close as possible, at the frequency that I desire to use it, which my main frequency of concern was 28.420 megahertz. And this is a frequency we have a local group that works on most nights, so that's why I wanted to use it there. And I wasn't having good luck talking to those guys with my other antenna. And the reason I made this to be one wavelength for the electrical length of this particular piece of coax was because the impedance gets repeated every wavelength. And I was able to put my antenna, and that also gave me a pretty practical height getting down to where I was going to attach the main coax that went into the radio. So I was able to put my antenna analyzer here and have a pretty good idea of what the actual antenna impedance was up here at the feed point. And that I think that, you know, I set this coax up, trimming it carefully with the antenna analyzer here to make sure that it had one wavelength of coax electrically, and I think it was around 22 feet or something like that. And this is a, you know, the velocity factor, I believe, come out about 0.65 when I measured it with my antenna analyzer, which is really close to the 0.66 that I see published. So, you know, that's probably pretty much good enough. Anyway, when I had the antenna analyzer here, and as I adjusted the length of all three of my elements of the antenna, I made it so it would be 6 inches or so long. And the first time, you know, it resonated kind of low. I trimmed 4 inches here, 4 inches here, 95% 4 here and here, and 105% here and here, because this driven element is half wave length, which I'm just going to call, and this is 0.95 times the driven element. I'm just going to call that D. And this is 1.05 times the driven element. And the spacing here for both sections is 0.2 wavelengths for a simple for the simple little 3-element dipole. And right now I think I'd like to probably going to trim a couple more inches here, but that's going to be a project I'll work with later. And overall, you know, I'm pretty happy with the result. I have I had a terminated antenna, which is a big loop with a resistor in it, and on this little local group that we gather most evenings and talk, there are a couple people that I couldn't talk to, and there's probably a few of them that I could talk to that didn't hear me very well, and pretty much everybody in the group I can talk to now, and none of them complain about my signal, and some of them I've gotten quite loud, and I notice that they get quite loud compared to before too. And I usually had the preamp on my receiver turned on, which I never use that anymore, which is nice because less background noise, less static, gives you a clearer signal. And what else? Okay, I've got 100 feet of coax into the radio, and I'm not using a high quality coax, so it has some losses. And you probably noticed where I was showing you the results of the antenna analyzer, that my SWR bandwidth became quite a bit wider when I put this 100 feet of coax in, which of course that's because of this coax that I have here is not really good. I'm probably getting about 2.5 dB of loss in that 100 feet. And even here, looking at the antenna, when I'm standing below it with this 22 feet, I've probably got 0.7 dB or something there of loss. So if I actually had my antenna analyzer right up here, the bandwidth would probably be a worse antenna. Well, I'm using a 1.51 SWR for my bandwidth. You can go further than that maybe, but for sake of not having too much signal loss and not having too poor a match to the transmitter, I decided that's where I was going to measure it. And so I'm probably broader banded here than I would be right there, but it wasn't very practical to try to climb up the ladder to check it, so that's kind of why I set it up that way. So I've probably got a total of 3.2 dB loss, which is actually about half of my signal, but considering that my other antenna was so ineffective, it was a big delta loop with a resistor in here and feeding it at the top. Easy to use. This resistor makes it very broad banded. I can work anywhere in the HF bands without using a tuner, but when you get down below 40 meters and down, this antenna really is not very good, though I have talked to Japan on it from the West Coast with on the 20 meter band. But this type of antenna is not very efficient. It's also not very effective because this Yagi antenna that I've built gives you a nice radiation pattern. It's kind of focused. You get more of your radio signal going in the direction you'd like to talk. Well, this kind of thing kind of bounces it all over the place, and I'm probably getting gain from the antenna itself, and that would be based on the feed point, not considering these losses here, but these losses here existed for this antenna and everything else too. So I'm probably the dipole itself, or the Yagi itself, I am probably getting the 5.5 dB over a dipole, or 7.5 or so, or 7 over an isotropic. So, but when I talk to people locally, because this antenna that I had poor, typically they're seeing my signal up by 9 S units, or not 9 dB, or even more than over this antenna. But remember, this was not a very effective antenna. It's so this little Yagi that I've built out of PVC pipe and wire is very, very big improvement over what I was using before. And I'm happily able to talk to everybody in the group, and most of them are pretty loud, and most of them tell me that my signal's much better at their house. I have not used it on a day when 10 meters open for any distance communication yet. I'm looking forward to trying that. I have one more thing I'd like to try. I'd like to make something, this big antenna out of PVC pipe is pretty floppy, and that's why I need all the stay. It also had my upright here that I told you about, and the cross of plywood that I have there. I also put some eyes in here. It's little lag bolt type eyes. So I had a little eye here, and a little eye here, and a little eye here, and I run guy wires, guy paracords basically, up to that aluminum plate to each of those, because I found that when I put the stays in there to support the outer reaches of the antenna, I found this thing tending to bow. Well, by putting them 4 guys for that vertical unit with the fiberglass rod in the middle, I was able to stiffen that up pretty good. And it's an interesting thing. It worked, but it was more. I'm happy with the results of it. I'm enjoying it, but it's probably not the same as a nice beam you'd buy, but it was a lot more interesting to figure out and do than a beam you might buy. I have one more thing I might like to try. I might like to build another one, very similar, but make all them cross pieces approximately 2/3 of the length of the half wave, and then let the ends of the wire droop. You take a dipole and you have a current distribution. I'm talking a dipole at resonance with a maximum right at the center and 0 at the ends. And you assume a sinusoidal distribution of that current in that antenna at resonance. And if you divide this about 1/3 of the way in each way, you end up with about 7% of your current in the ends, and about 86% of your signal current in the centerpiece. So if you droop the ends 1/3, you're going to end up with about 7% of your signal being in this section, and about 86% here. So I would think that this 86% would be basically a horizontally polarized signal. I'm going to draw the horizon, so that's the way that this is sitting here. And these would be vertically polarized. But 86% is approximately equal to minus 0.65 dB. So you would lose some signal in the horizontal component that way, but the idea of trying this is to make an antenna, if instead of being 16 feet long, it's about 11 feet long or wide, not quite so floppy, and on a setup like that I might be able to, you know, guy it halfway out and maybe leave 3 foot hanging out here. So that's something I might like to try sometime. I've had a lot of fun with this project, and I hope those of you who watch this video enjoy it, maybe think about building something yourself. I mean, the design equations for this simple 3-element Yagi are all over the place. They're simple, and you know, you could use different types of supports. You could make a boom out of wood. You could use bamboo cross pieces. There's all kinds of ideas you could come up with, and you might have a good time with it. I hope some of you are encouraged to do some experimenting of your own and come up with your own ideas after watching this video and such. I made an experiment myself one time quite a few years ago where I had a 10-meter dipole, and it was about a half wavelength up above the ground, and I had a vertical 10-meter dipole that was probably not quite a half wavelength. The center of it was probably about a half wavelength, but it probably would be better if the bottom of it was a half wavelength. But anyway, I was talking on 10 meters across the continental United States from the west coast to the east coast, and I had an antenna switch rigged up, and I did an experiment. Well, the guy on the east coast could not tell the difference in my signal on the half wavelength horizontal dipole or the half wavelength vertical dipole. So this is why you've probably seen in some of the antenna articles and stuff, if you have compact space, they tell you have as much of your dipole horizontal as possible, but it's okay to droop some of the ends. And you know, 7% of your signal from each end and 86% here, you still have useful signal going out. And by the time you locally, this would probably pretty much break up that way: 7% vertical polarized and 86% horizontally polarized. But by the time you talk long distance and your signal is refracted off the ionosphere, or refracted by the ionosphere, this here vertical and horizontal polarization tends to get jumbled up. So when you talk long distance, you might not see much difference between this and this with 100% of it horizontally. I know in the experiment I did, between completely horizontal to completely vertical, and that was talking, you know, 3,000 miles or so, the individual on the other end could not detect a difference in my signal when I tried the other polarization. And I'm sure you've seen some of the antenna books where they talk about, you know, if you're short, you got a limited length spot or something, feel okay with drooping the ends of your dipole antenna. And the one thing you got to be concerned about that, you know, we got the current distribution like that, but we have a voltage distribution that looks like this, with high voltages at the ends. So you don't want these ends where somebody can get their fingers on them, get an RF shock from, I'm just going to H, so I'm going to say high voltage. And the same thing here. And of course you see positive, negative. The value of the voltage on each end is the same, but the polarity is opposite, because that's what gets your electrons flowing back and for your charges back and forth, you know, opposite polarities. But so that's one thing you want to consider if you drop your dipole like this. Say you had a hidden dipole up in the attic, you wouldn't want these ends to be touching where you might have wet wood and maybe get some arcing and maybe even start a fire with that. So it's not. The antenna will work pretty good, but you want to consider the high voltages that appear at the end and make sure you've taken precautions. If you got the antenna 20 feet in the air, then you hang it down here, 3 or 4 feet, it's still going to be 17 feet in the air. Nobody's going to be touching that. But if you're in a situation where you can't put an outdoor antenna and you got an antenna at the hidden in your attic or something, I would recommend you make some way, maybe space that end out so it's not touching anything. Anyway, I hope you've enjoyed this, and I'm going to close this with some video of the final installation that you'll be able to look at. And like I said, think about your own ideas. Use them formulas. They're not hard to find, and they're in the early part of this video anyway. But think about your own way of supporting it. An example, you could literally make those 3 pieces out of wire, and you could just tie that to some rope. Maybe have a spreader here. Maybe you could tie it up in some trees and you couldn't turn it, but maybe you could set up a dipole for portable operation very, very quickly and simply. I think people have done that. Or if you're in a situation where you could say you want an attic antenna, but you really couldn't have nothing outside, you could just string these 3 wires in your attic space properly. Lots of things you could do. And I think you probably see this in the video, but my wires, because of the stays and stuff, each of the PVC pipes did end up kind of bowed. I just run the wire on the top and taped it with electrical tape every foot or so. And I did keep the end of it kind of kicked out away from the plastic pipe, simply because the high voltages that appear on there, and I didn't want, if it's wet or anything, for that to mess up the antenna operation and such. Anyway, come back again and enjoy the remainder of this video where you'll see the final. Oh, I did one more thing I want to talk about. Forgot this. I want to show you what I did for a mast. When I was building this antenna, I wasn't sure what I was going to do, but by the time I got done with it, I decided I dug a hole in my ground, post hole digger, that is, I think I made that about 32 inches deep. And in the bottom, I put a couple inches of pea gravel. And I have a 10-foot piece of, this is just 2-inch galvanized water pipe. And the reason I put the pea gravel in there is because the top of this is open. Water could get in it. I want it to be able to drain out. I filled it in here with concrete. So the pole is concrete in the ground, but it's got this pea gravel at the bottom to allow any water to seep out into the ground eventually. Inside there, I put about 8 inches, just dumped it down the top of the pea gravel. And the reason I did that is because my next piece going up, this is 2 inches, and I put a piece of 1.25 inch pipe in the middle. And I didn't want that to fall down inside where I couldn't get a hold of the top. That's why I filled the pipe partially with pea gravel. And I added the floor flange I showed you across the top of this thing, which bolted to those fiberglass, or not fiberglass, the wooden cross piece with lag bolts. So I had this antenna when I was assembling it, and to let it down to trim the ends and stuff. I think it was about I think I'm about 8 foot off the ground, something like that. And I can go up, I think I'm about 8.5 feet here to the top of this, to this point. I got about 7.5 feet here and another foot or so here with the pea gravel inside there. And I can push this up to, I think it's a little over 16 feet. In my 1.25 inch piece, I put the flange on the top. I drilled a hole through the thing about 1.5 feet through the end. So I can let it down. I can stand on an ordinary size step ladder. I can adjust the antenna, play around with it. Then I push it up. The whole antenna weighed 33 pounds. That's without the pipe. I imagine that pipe's another 15 pounds. So I'm probably pushing up somewhere in the neighborhood of 50 pounds. Push it up, and then when I get this hole above the top of the 2-inch pipe, and this is 1.25 inch, this smaller one. Pipe, 1.25 inch pipe. When I get the hole above the top of this one, I got the screwdriver in my pocket. I just shove it through this hole, and that you could use a bolt or something. I just use a cheap screwdriver that had laid on it. That keeps it from falling back down in. So it's a pretty solid mast made out of galvanized water pipe, but it only goes up a little 16.5 feet or something to the top of this thing. So it's very close to half wavelength in height, but maybe a few inches below that. Anyway, hope you all think of some ideas, enjoyed this video, and maybe you build some antennas of your own. Thanks for coming and watching, and enjoy the remaining, which is going to show you the final installation.
So here is the 10-meter PVC pipe and wire, 3-element Yagi that I've put in place. You can see each of the elements, and I'll try to get a little closer look here to help you see what's going on with the thing. Let's see if I can zoom in a little bit there. You can see that I've created this cross on a 2x4s to give it a little support. It's pretty floppy, but you know, it works. There's the mast, and there's where the mast goes down into the 2-inch pipe, 1.25 inch pipe. I got a screwdriver stuck through a hole to kind of hold it up there. I can get up on the ladder a little ways, only about 5 feet, and turn the thing. So do a little zoom back in on there, and maybe you can see that I have a choke in my coax wound up to feed it. The center element I'm feeding is just a dipole. I've got it broken 2 pieces with the shield of the coax going to one half and the center of the coax going to the other. Soldered it on there and insulated it with natural rubber tape and with vinyl electric tape. And there you can see I have the upright with all them little parachute cord stays to add some stability to it. It's pretty floppy anyway, but that may be all right. Maybe if it flops around the wind, it won't break. It's in a fairly sheltered location. We'll see how it does through the winter, but for right now, it seems to be working pretty good. I'm having a good time getting out better than I did before, and I hope you guys all enjoy this video, and we'll give you some more stuff in the future.